Okay, I'm going to talk about an integral, and we're going to talk about how to evaluate integrals in spherical coordinates. Okay, so the key ideas are to draw the region of integration in both xy and rz planes. I think if you do this, then it's a lot more clear what's going on. Just do not do 3D stuff. Do not even try 3D stuff. It'll give you a headache trying to make it look not cluttered. And then the second thing you do is I like to write arrows to indicate the integration order and the region boundaries. Again, this is just stylistic. You don't have to do this if you don't want to, but I'm just trying to give you a nice way to get all this onto diagrams and paper because it's simpler, in my opinion. Okay, and the role of spherical coordinates is to simplify the limits. So the role of spherical is to simplify the limits. So for example, if you're doing things on a rectangle, you should not use spherical coordinates. That will make your life so much harder. So let's talk about how to do one of these integrals. Let's take the 0 to 2, and then we'll go from 0 to 4 minus y squared, and then square root of x squared plus y squared, and then to 8 minus x squared minus y squared, and then our integrand will be z times dz dx dy. And try not to get freaked out by how big this expression is. It's not as bad as it looks. It'll turn out to be quite an easy integral once we process it with coordinates. So, step 1, draw this thing in the xy and rz planes. So I would look for the outer integrals because that's the ones that we're integrating in. So the outer integrals will tell you how to draw these things in the xy plane. So the outer integral tells us that y ranges from 0 to 2, and x ranges from 0 to the square root of 4 minus y squared. Really, this is just the circle of radius 2 in the first quadrant. Okay? So x, y, draw a circle of radius 2. And I'll just draw these. I'll just draw some arrow to indicate this is the region inside the circle. So now we look at the RZ plane, and we'll look at the innermost integral. Okay, now z is ranging from that square root to that other square root, and we know that if you see square roots and x squareds plus y squareds, that we should immediately think spherical. Because this should hopefully make our life a lot easier. So if you now place this in R, then the lower limit is R, the upper limit is 8 minus R squared. So really this is just the circle of radius square root of 8. And if we plot this now we have our circle of radius 8 square root, and then we have our lower curve, which is just R. Okay, so this is rho equals square root of 8, and this is z equals R. Now, in spherical coordinates, we know this is rho equals square root of 8, and then we know this one is rho, let me just quickly derive this. So z equals R is rho cosine phi equals rho sine phi. Let me just redraw our diagram. And you should also draw this thing. Just it's very quick. It took me 3 seconds to draw that, but it'll just clarify and make sure I don't make a mistake. So we cancel the row. We get phi equals pi over 4. So the lower limit corresponds now to phi equals pi over 4. Okay, so we started out with this integral. Our arrow was going from the lower r to the top one. So in spherical, now I will redraw this diagram. And this seems pedantic, but I think it allows for less clutter. So, and we see now we're not actually integrating from two different functions. We're integrating now from the origin to the radius. So our d rho actually just goes from 0 to 3. So rho now ranges from 0 to 3. Oh, I'm sorry, square root of 8. And our phi also changes. I'm sorry. What we have now is that our phi is ranging from 0 to pi over 4. So what did I just do here? I noticed that our integration in z, it was not meshing with spherical coordinates. So what I did was, I said, how do I draw this cone, or this region, in just spherical coordinates? And what does that mean my integration has to be? Well, the integration, rho, it can only go from 0 to the outer curve, and our phi is restricted just to from 0 to pi over 4. So, in fact, this is actually much simpler because now our integration limits are constant. Constant limits. Okay? So, and also let me just, the fact that let me just go back to the xy plane for a second. The fact that we're in the first quadrant, that means that theta is restricted from 0 to pi over 2. So we don't have to do anything here. Our theta work was pretty easy. So let me just indicate the limits again. Rho was going, I'll just draw the diagram really quickly. Square root of 8, pi over 4, and our theta was from 0 to pi over 2. So rho goes from 0 to square root of 8. Phi goes from 0 to pi over 4. And theta goes from 0 to pi over 2. Okay, so now what I do is just put my integrals using these new coordinates. So in this case, they're constant limits, so I can actually order them however I want. I just like putting theta on the outside usually because it's very typical theta has no role. So I'm just now going to put these ranges on the integral signs. And now we have just the same integrand, which was just z. So z is, in fact, rho. If you need to do the diagram helps me at the very least. So it's rho cosine phi. So I'm just going to put rho cosine phi here. And now our dv will be rho squared sine phi d rho d phi d theta. Okay. Now, constant limits allow us to split. Or you can call it factor. So I'm going to factor this into first the theta integral, 0 to pi over 2. There is no theta integrand, it's just d theta. Now I'm going to do the phi part, 0 to pi over 4, that was the phi limits. So now we have cosine phi, sine phi. Cosine phi is the z integrand contribution. Sine phi is the volume contribution. Finally, we have rho going from 0 to square root of 8. And we'll now have rho cubed d rho. That's it. Now this is easy. Okay? So I think the hardest part is just setting up the integral. And so what you need to do is just write all the ranges in spherical coordinates. And make sure the region is captured by those ranges. Okay? So I think if you just follow this recipe, you'll be able to integrate anything you want in spherical coordinates. Okay, thanks for watching.